We'll begin this third video cast with a quick review of things we've learned thus far in Chapter 5. Make sure that you have a pen or a pencil available and a blank piece of paper to write down some notes of some things that are a brief review of everything so far in Chapter 5. Thus far, Chapter 5 has talked about energy. The measurement of energy in the metric system is done by a unit called the joule, or the larger unit sometimes called the kilojoule. The joule is represented by a J, capital or smaller case j, and a kilojoule is represented by a small k and a capital J or small k and a lowercase j. The amount of energy needed to raise 1 gram of water 1 degree Celsius is 4.184 joules of energy. And this amount sometimes becomes very critical because it turns out to be something called the specific heat of water that we'll look at in a little while. 4.184 is a number you end up usually memorizing. When we talk about energy in Chapter 5, we talk about defining the system that we're talking about and the surroundings that are all around the system. The system we talk about in chemistry many times are the atoms, the molecules, or the ions, or the particles that make up the thing that we're looking at. In the case of chemistry, it would be the solution inside the beaker and the atoms or the molecules that are in that. The surrounding would be the beaker, the thermometer that's in the beaker, the air that's around the beaker. And what we want to know is what happens to the energy as it flows from the system to the surroundings, or from the surroundings to the system, one or the other. If it flows from the system to the surroundings, we see that the change in energy is negative. The system has lost energy. If it flows from the surroundings to the system, we say that the change in energy is positive. Two different types of energy that we primarily see in chemistry are heat energy and work energy. Heat is the one that we see 99% of the time. Work energy is equal to force times distance, and we see that occasionally when we see something pushed or pulled, and in most cases is when we have a piston or some type of gas that's expanding that's causing a pushing or a pulling. We're not going to work with work very much here today. We're going to focus mainly on this type of energy, heat energy that's transferred from a system to a surrounding, or from a surrounding to a system. When we have heat and it's either given off or taken in, we usually symbolize it by the letter Q. The small letter Q is negative if heat is lost by the system. These are called exothermic processes or exothermic reactions, and it's positive if the system gains heat or gains energy. These are called endothermic processes. Well, when heat is transferred at constant pressure, we give this heat energy a new name. We call it enthalpy, and we now change the symbol to mean the symbol from Q to H. And we don't usually measure directly the enthalpy of a system, but we measure the change that the system undergoes in terms of enthalpy. This triangle right here is a Greek letter delta, which means change. And so from now on, for the most part in this chapter, we'll talk about enthalpy changes, or heat energy at constant pressure changes. So Q and H are similar, and they're exactly the same as long as we're at a constant pressure. One of the ways to find out, well, one more thing here. Q, remember, is equal to delta H and is positive or negative, whether the system has lost energy, negative, or the system has gained energy, positive. One of the ways that we can determine the amount of enthalpy gained or lost by a system is looking at what's called a thermochemical equation. Here's an example of a thermochemical equation using A and B as reactants and C as a product. And in this case, we write delta H, or triangle H, meaning enthalpy, is equal to negative 100 kilojoules for this process. And this process tells you that for 1 mole of A, because there's a coefficient of 1 in front of it in the balanced chemical chemical equation, 100 kilojoules of energy are released. For 2 moles of B, 100 kilojoules are released. For 3 moles of C that are created, 100 kilojoules of energy are released. The reason I know that it's energy released is because it has a minus sign right here. And remember, the system are the chemicals, and the system is losing 100 kilojoules. If it had a positive value, I'd say it's an endothermic process, and the system would be gaining energy. And remember, this speaks to the change that's going on from reactants to products. When this occurs, a certain amount of energy is either lost if it's negative or gained if it's positive. So that's one way. That's one way you can find enthalpy. A second way that we looked at in our last videocast was to use a calorimeter to determine the energy gained or lost by a system. A calorimeter that is open to the atmosphere is called a constant pressure calorimeter, and there's an example of one of these that uses simply a coffee cup on page 185 in your textbook, and you can see that this is merely 2 coffee cups stacked together. It's got a stirrer and a thermometer, and we did a couple of sample exercises with that last time. A second type of calorimeter that we'll look at in this video cast is one that's called a bomb calorimeter. A bomb calorimeter is talked about on the next page, and it's figure 5.19 in your textbook on page 186. And I'm going to zoom in on this just a little bit so you can take a closer look at a bomb calorimeter. And you can see in this case a bomb calorimeter is a device that is used to measure heat accompanying combustion reactions, and they occur at constant volume. Now, we've been talking about thus far in this chapter mostly heat energy that occurs at constant pressure. In this case, this is a container that could contain a large amount or a large change in pressure. And so technically what you're determining with this bomb calorimeter is the change in Q. The change in Q, the change in heat energy, not the change in delta H. Because remember, delta H is only equal to Q when you're at constant pressure. And this container, a bomb calorimeter, would not always be at constant pressure. But, and this is a big but, bomb calorimeters lots of times use only small amounts of substance, and therefore the change in pressure is not that great. And so we can effectively approximate H by using a bomb calorimeter to find Q. And so they are very similar to one another, even though it is a constant volume calorimeter, not a constant pressure one. And so we'll assume that it's the same right now, but knowing the difference is important. You can notice in this picture we have a cup that holds a sample. The cup is surrounded by water, which will absorb the heat that's lost when the combustion occurs. There's an inlet for some oxygen to be added. It stirs the water right here. A fine wire comes in contact with the sample and therefore ignites it and burns it. You can see that the thermometer can check the change in temperature of the surrounding water. And so bomb calorimeters are effective in determining the enthalpy change for combustion reactions. And you can read more about them here on page 186. And if you would please take a moment right now and find your sample problems, and we're going to work 2 sample problems that use a bomb calorimeter. The one I'd like you to find right here has methylhydrazine as the first sample problem. And the problem says methylhydrazine, CH6N2, is a commonly used liquid in rocket fuel. The combustion of methylhydrazine with oxygen produces nitrogen, carbon dioxide, and water. And it gives the balanced equation right here. Then it says when 4 grams of methylhydrazine is combusted in a bomb calorimeter, the temperature of the calorimeter increases. In a separate experiment, the heat capacity of the calorimeter is measured to be 7.794 kilojoules per degree Celsius. What is the heated reaction for the combustion of 1 mole of methylhydrazine? Well, the equation for a bomb calorimeter is a little bit different from the coffee cup calorimeter equation, and yet it's still similar, where we can say that Q of the reaction is equal to the heat capacity of the calorimeter, and we put a negative sign in front of that because it's the heat that's given off by the substance to the water inside of the calorimeter, times the change in temperature. And remember, this is going to give us the heat of the reaction that is approximately equal to, I'm going to just put this as kind of approximately equal to, the enthalpy of the reaction, because we're assuming that the pressure change is not that great. And it's also going to give us the enthalpy change in amount of energy per mole of reactant or substance. So in this equation then, what we can do is we can take our heat capacity that was determined before, 7.794, and put that in for the heat capacity, CAP, as 7.794, and the units on that are kilojoule per degree Celsius, and don't forget I have a negative sign right here. And then I'm going to multiply that by the change in the temperature. And it tells me that my change in temperature was from 25 to 39.5. And so I'll put in the final temperature, 39.5, and subtract from that the initial temperature, 25. And when I do this temperature change right here and multiply it by the heat capacity, I end up with a Q right here of negative 113 kilojoules. Now I have to go back and just take a look at what the question's asking me again, because it asks me in here, what is the heat of the reaction for the combustion of a mole of the methyl hydrazine right here? And if you look at the question, it says this is for 4 grams of the sample right here. So this is how much energy on negative 113 kilojoules is given off for 4 grams. And so I need to convert it to the amount of energy that's released per mole. So if I know that for every 113 kilojoules that are released, there are 4 grams of the methyl hydrazine that are burned, I can take and I convert this from grams to moles by putting grams in a position where it's going to cancel and putting moles as my new set of units. And this is grams of methyl hydrazine, which has the formula CH6N2. CH6N2, grams of CH6N2. Notice my grams would cancel with my grams, and then I need to go back and remember way back from chapter 3, how do I relate grams and moles? Well, if I look on the periodic table, I can add up 1 carbon, 6 hydrogens, and 2 nitrogens, and I find out that in 1 mole there are 46.1 grams of CH6N2. Carbon, remember, if you look on your periodic table, has an atomic mass of 12. Nitrogen, of which there's 2, is 14. And remember, hydrogen has an atomic mass of 1. And if I add all those together, I get 46. And if I multiply that together, I'll end up with negative 1.30 times 10 to the 3rd kilojoules per mole of methyl hydrazine, which is the answer to the question that they wanted to know, because they wanted the heat of reaction for the combustion of a mole of the methyl hydrazine. Well, if you take a moment and you back up in your practice packet, you go back to practice exercise 5.7 on page 187, one we skipped before. And this is actually a bomb calorimetry question, even though they didn't say that it was a bomb calorimetry question. So take a moment, pause the video now if you need to, and find this practice exercise. It says a 0.5865 gram sample of lactic acid is burned in a calorimeter, and it should say bomb calorimeter, although it doesn't in the question, but that's what it's illustrating, whose heat capacity is 4.812, and the temperature is increased from 23 to 24, indicate the heat of combustion of lactic acid per gram and per mole. Well, to solve this problem, we use the same equation that we just did. Q is equal to C sub cal times change in temperature. And we're told that the heat capacity of the calorimeter is 4.812 kilojoules per degree Celsius. And we're told that the change in temperature goes from 23.1 to 24.95. And so I need to multiply by the final minus the initial in degrees Celsius. Notice the degrees Celsius will cancel with the degrees Celsius, and I will now get my, don't forget the negative sign right here, now get the heat, or the heat change for the 0.586 gram sample in kilojoules. And then I can take this number that I get as the Q, and I need to know it per gram. So I'll take this number and divide it by 0.5865 grams, which is the amount of my sample right here, to get my amount in kilojoules per gram. 4.812 times my change in temperature, 24.95 minus 23.1, should give me about 8.9 approximately, and then I take that number and divide it by 0.5865, and I end up with a heat capacity, notice the negative sign right here, so it's going to be negative, of about negative 15.2 kilojoules per gram. It also asks me in part B to find it per mole. And so now I'd have to do the same thing that I did in the last sample exercise and change it from grams to moles of the lactic acid. And so I have to add up lactic acid on the periodic table and find out how many grams there are in a mole of that. And if you want to try that, you certainly can. The answer turns out to be negative 1,370 kilojoules per mole. So those are two examples of using the bomb calorimetry equation. And just as one quick wrap up, I know you're allowed to use one of these yellow periodic tables on your exams all the time. If you take a look underneath the thermochemistry kinetics area, it'll give you the equations that you use in a little bit different format for the calorimeter type problems. You can see right here is the Q equals MC delta T equation. Our book uses, instead of a small c right here, they use a small s for specific heat. M is mass, and triangle T, of course, is change in temperature to find Q, and they don't put delta H there, but remember it's delta H as long as you're at constant pressure. And then here's our heat capacity equation right here. Notice they put in delta H right here, assuming that your bomb calorimeter would be not just Q, but approximately delta H, and they take away the negative sign there as well, assuming that you know that heat is released by the substance that's combusted. So those two equations are given here in a little bit different format than they are in your book, but they're both available to you on the periodic table. So good luck with your calorimetry and bomb calorimetry problems.